Hi everyone, and greetings from Saarbrücken, Germany. I'm going to present our paper on Coq mechanizations of Sierpinski's theorem that the generalized continuum hypothesis implies the axiom of choice. This is joint work with Felix Rech. So let me first clarify the statement. The generalized continuum hypothesis is a set-theoretic principle that asserts that there are no cardinalities between an infinite set and its power set. So more formally, this means that if I have an injection of the natural numbers into some set x, so by this x is infinite, and I have a second set y, which is squeezed in between x and x's power set, then one of these comparisons must be invertible. So either y is below x, or the power set of x is below y. Secondly, the axiom of choice, of course, has many equivalent formulations, and the one working best in this talk is that every total relation contains the graph of a function. So if I have a binary relation, which is provably total, then there exists a function that is contained in the relation. Let me now give you a brief outline of the standard argument, how this theorem is obtained. So the first idea is to not prove AC directly, but to prove the equivalent well-ordering theorem, which states that every set can be well-ordered. Then secondly, it always suffices to well-order, if one wants to well-order set X, to find a larger set Y, which is well-ordered, because well-orders transport back along injections. So in particular, it is enough to just look at the infinite sets, because every set can be embedded into an infinite set. This means we just have to show, assuming GCH, that every infinite set can be well-ordered. And this remaining proof can be split in two halves. One half is a central construction, the so-called Hartogs number, which is a large well-order, large in the sense that the Hartogs number of a set cannot be injected into the set anymore. But this height is controlled in the sense that the Hartogs number is bounded by the k-fold power set, where k depends on the actual construction we use. Now, having this notion of Hartogs number, the rest of the proof depends or can be done by using GCH iteratively, in fact exactly k times, to squeeze in the Hartogs number and to finally obtain that x injects into its Hartogs number. By this we can transport back the well-order and have well-ordered x. So this is the main outline. Now, of course, if we want to mechanize such an argument in Coq, we first have to find formal representations of all the notions involved. And actually, there were not that much notions involved in the previous outline. So we just need something for the power set. We need natural numbers, relations, functions, cardinals, and orderings. And since all of these notions are pretty abstract, we actually have two strategies how this can be mechanized in Coq's type theory. The first strategy is the probably expected one. Coq's type theory is expressive enough to formulate the axioms of some variant of set theory, and in this axiomatization we can work. However, there's also the second strategy. We do not axiomatize an intermediate notion of set theory. We just use Coq's type theory itself, because Coq can represent all of these notions. And in our paper we do both. And why do we do both? Well, the first strategy is a good case study of how set theory is best represented in type theory, because there are many different approaches. And the second approach, or the second strategy, just highlights the fact that on a very high level, those two views on foundations of mathematics become pretty similar. And so many results from one foundation can be transported into the other foundation. Let me now give a little overview, a glimpse of how these two strategies are set up. The first set-theoretic strategy is set up by axiomatizing a type of sets. So we assume a model in the sense of a type representing sets plus the necessary structure of the Zermelo-Fraenkel axiom. So we need a membership relation and then operations for pairing, union, power set, empty set, and an infinite set. And now in Zermelo-Fraenkel set theory, there's also one more axiom, the axiom of replacement, which is typically formulated by a first order scheme. So for every binary first order formula that can be shown functional, so a formula phi with two variables, it is possible to, given any set y, form the set of all x's for which some set exists such that z and x are in relation in phi. This way to represent replacement is of course a bit hard, because this first requires to make a nice first order logic. We have to have a clear notion of the syntax to formulate these formulas phi, and we need the semantics so that satisfiability in this model can be explained. And this is of course work one has to do, but it's also work that is actually not really necessary to do, because logic is of course present in Cox type theory, and it would be nice to just reuse it. And this is exactly done in a higher order formulation of the replacement axiom, where we just allow forming the replacement set for any functional relation on the type of sets, not just the first order definable ones. And this is more convenient to work with in already two ways. The first way is because this statement is really easy to write down. We don't have to presuppose some notion of first order logic for it. And it's easier to work with it, because always when we apply it, it suffices to write down a relation in Coq, which is easy to do. And we don't have to write down a relation as a first order formula, which would be harder to do. And we can now even use more of Coq's expressivity to streamline some other axioms, and by this get a rendering of higher order set F that is really convenient to work in. So let's look at the second strategy. This strategy was based on the general fact that many set theoretic results can actually be rephrased in type theory. This has, for instance, been done for the equivalence of the well-ordering theorem and the axiom of choice. In our setting, using Cox type theory is a really good match, because in Coq we also have this impredicative universe of propositions, which makes the type theory even a bit closer to set theory. So in fact, what we have is a type of unary predicates, which can always be seen as a power set. And we have a notion of anonymous propositional existence, which for instance can be used to define propositional cardinality comparisons. So based on the hidden existence, anonymous existence of injective functions. And moreover, the type theory is still consistent with assuming a principle like unique choice, which is somewhat hardwired in set theory. And by assuming this in Cox type theory, we make the setting even closer to set theory. Now in this setting, if we want to tackle something like Sierpinski's theorem, we have to know how to represent GCH and AC. And we can do this by the following two propositions. So this is just GCH as stated informally before, and I've highlighted the things that need more explanation. What do we quantify about, and what is the power set? And with what I have said above, it is clear we can quantify over all types, because in this interpretation, the sets are just the types, and the power set is the type of unary predicates. And similarly, for the axiom of choice, we have to clarify what we are quantifying over, and we're quantifying over the type theoretic notions of binary relations and functions. Okay, so the situation can be summarized as follows. There are three levels of set theory present in Coq. There's the very low level of first order set theory, where we have an axiomatized first order type of sets, and all notions of set theory are encoded in the usual set theoretic fashion. On the other end of the spectrum, we have type theory with its abstract notions that are expressible in the meta language itself. And in between, we have higher order set theory, which is kind of a bridge between both worlds, because we do have the set theoretic operations available, but they will always coincide with the type theoretic notions that are also available. For instance, an axiomatized set or power set operation, higher order set F, will always be isomorphic to a unary predicate type. So this can be summarized paraphrasing a famous quote of Quine, that higher order set F is type theory in sheep's clothing. So what have we exactly done in our paper? We are not the first to mechanize Sierpinski's result in a proof assistant. This has been done already by Mario Carneiro using MetaMath, based on the library of first-order set theory. What we do in COC is we synthesize 3 alternative proofs. We work in COC using axioms. We extend COC with extensionality and classical logic to make it easier to mechanize set theory. And the first variant we do is we mechanize Sierpinski's theorem in a higher order axiomatization, as explained before. And then there's a second version where we prove Sierpinski's theorem as a type theoretic result. First in the variant where we further assume unique choice to make our life even a bit more easy. And then we show that this last assumption is inessential. And our take home is that COC is a proof assistant which is well suited for such a project because we do have axiomatic freedom in the sense that it's easy to assume classical logic, and even the standard automation tactics will become aware of it. You can further add extensionality, unique choice. And also COC is a mature proof assistant, so all its helpful features could be used to make the developments easier. For instance, we use type classes, set-rate rewriting, and auto-rewriting. So our COC code plus the paper and HTML documentation can be found on this link. In particular, if you want to have a look at it, I would advise you to start at the paper, then you can click on any statement, and this will bring you to the HTML documentation. Okay, so now in the rest of the talk, I want to explain to you the proof of Sierpinski's theorem more formally, and I will do the first half in higher order set theory and the second half in the type theoretic setting. So let's start with higher order set theory. Again, as mentioned before, we work in a model providing the necessary structure. And on this model, we impose the axioms of higher order set theory. And the 3 axioms that differ from their first order versions are the axioms of foundation, where we state that every set has a well-founded membership relation, where well-foundedness or accessibility is expressed as an inductive predicate. The infinity axiom is formulated with reference to the external type of natural numbers. And the replacement axiom is stated, as mentioned before, for all functional relations we can form, and asserts the existence of a set representing this class. So the class of the replacement set. Okay, I won't explain a lot of set theory developed in the setting. Most of it is really standard and it doesn't matter that much. The just important thing I want to highlight is that higher order replacement induces a unique choice operator. So on the type of sets, we do have unique choice in the form of an operator delta that for a uniquely satisfiable predicate returns an exact value of this predicate. You don't have to look at this in detail, it just should show that in one instance the replacement axiom is really needed, the rest is standard. And what does this mean? Well, having unique choice available just tells us that we are really doing set theory here, where there is no difference between a total functional relation and a function. So now we want to do the first half of Sierpinski's theorem, which was based on well orders. And in set theory, we are in a lucky situation because we have ordinals, which are a canonical representation of well orders. And the way how we can formulate ordinals in our setting is by an inductive characterization. So first we call a set transitive if every of its elements is a subset. And then we say that a set is an ordinal if it just contains ordinals and if it's transitive. So this means we can here use an inductive predicate to directly express something that is a bit more cumbersome to do in first order set theory, where one normally defines ordinals like something like sets with well ordered by membership that are transitive. And the advantage of having this definition is that by an inductive definition, we already get an inductive elimination principle, so we can do proofs by induction. that are a bit more direct than proofs that are on the secondary definition available in first order logic. Let me just quickly say that there's also alternatives. So one instance could be to use 3 inductive rules that make the constructors, the empty set, successor, and limits more explicit of the ordinate structure. But independent of which definition you choose, the intended results about ordinals, namely that they are well ordered by membership and that they uniquely denote well orders, so that order isomorphic ordinals are equal, those results are by simple induction on the ordinate structure. Okay, having this notion of ordinals, we can now look at the construction of large ordinals, so ordinals that satisfy that they are not injectable into a set we start with. And in our setting, we can define the Hartogs number of a set A as a particular class, so the class of all ordinals that inject into A. And now we have to verify the intended properties, and we do it in this order. So first we want a bound on the size of the Hartogs number. We want that it is an ordinal, so in particular it's well ordered, and we want that it's large. And the first part is by some standard construction showing that the ordinals that are injectable into A can be actually represented within A as well-ordered subsets of A, and this will induce this particular bound. The second part then is straightforward by the definition of ordinals, using our inductive characterization from before, and the third part is straightforward by the very definition of the Hartogs number. So the proof here is really compact and uses the set theoretic notion of ordinals a lot to give us access to even larger and larger well orders. And this already finishes the first half of the proof, and we now switch worlds and look at the second half of the proof. So we are now in a type theoretic setting, and we should first clarify that what we have done so far can be somewhat simulated here. And of course, the problem is in Cox type theory, if we do not further extend it with more extensionality axioms or quotients, we do not have something like ordinals. So there is not the easy structure available to represent well orders, and we have to do something different to obtain large well ordered types. And what we do is basically what we do in the first part of the proof here. Instead of looking at an abstract notion of ordinals, we just look at small ordinals that can be represented within a given type. And this representation can be understood as follows. So first we can look at the power type of X, which can be seen, so the elements in it, the unary predicates, can be seen as subsets of X. Then we can look at the twofold power set. Elements of this are sets of subsets. And on these sets of subsets, there's a canonical ordering, namely inclusion. And some of these sets of subsets could even be well ordered. And now if we add another layer of power types, then we have classes of sets of subsets. And some of those might happen to be equivalence classes of well orders. So well-ordered sets of subsets as before. And those particular equivalence classes are called small ordinates. And we can isolate them in the subtype h of x, which exactly contains the small ordinals within our starting type x. And now we can verify that this type h of x has the expected properties. So it is well-ordered, it is large, and it is large in a controlled way. And those proofs are now really a bit harder than the ones in set theory, because here we do not work with an abstract notion of ordinals, but with an internal representation. Okay, so now having this in place, we can look at the remaining work to do. So we want to prove now that GCH implies AC. And as explained in the outline at the beginning, it is enough to show that every infinite type is well orderable. And to show this, we now create a situation where we can apply GCH, and the situation is as follows. We look at the two-fold power set of X and the three-fold power set of X, and in between we squeeze the sum type of the two-fold power set of X and the Hartogs type of X. And this situation is created because from left to right, we can of course inject into the sum if we just take the left injection. So this injection is clear. And from the middle to the right, we use a lemma, and we will talk about this lemma later. What it says is that infinite types have particular properties, and along these lines that adding something to the types, in particular doubling the type, does not change the cardinality anymore. By applying this lemma, it's not important how this works in detail. We also get this comparison. So now, if we apply GCH to the situation, recall that this means that one of these comparisons can be inverted. So let's first assume the first comparison could be inverted. So the sum is already below the two-fold power set. Then in particular, the Hartogs number of X must be below the two-fold power set. And this means that we have decreased the bound on h of x. Before it was bounded by the three-fold power set, now it's bounded by the two-fold power set. And this means we can iterate. And after maximally 2 more steps, we will be done. Now in the second situation, we have that the three-fold power set is below the sum. And in this setting, let's look at what's going on here. So we have the two-fold power set here, and the power set of this is below the full sum. And because we know by Cantor's theorem that between the power set of a type and the type itself, there is a huge gap in cardinality. This means that this half of the sum does not contribute much to the cardinality of the sum. And in fact, we can just leave out the half here and get that the threefold power set must be below h of x. And then we would be done, because x, of course, is below the threefold power set of x, and so x can be well ordered in total. And the lemma we have used here, just to repeat it, is really not much more but Cantor's theorem. So whenever we have a power set of x below the sum of x and another set y, and there's a side condition on x, then this half of the sum is inessential, so then already the power set of x is below y. Okay, so now the only thing left to clarify is the first lemma we had on infinite types. So look at it again. The form is that if we double the power type of it, then this does not increase the cardinality in comparison to the power type itself. And for this, we in fact need to extend the type theory even a bit more. So now we need, this is the crucial place where we now first assume unique choice. Unique choice in the form that every uniquely satisfied predicate admits a concrete value we can work with. And now in this setting, we can see that we can define a lot of invertible functions in type theory. And you don't have to look at them in detail, I just want to make the point. Many invertible functions are definable without appealing to unique choice. For instance, that the natural numbers are in bijection to the sum of unit and the natural numbers. But on the other hand, a lot of bijections are not definable in Coq right out. So here you would need unique choice and excluded middle that we assume anyways, for instance, to show that Booleans and propositions coincide. And now it is possible to just generate enough of these bijections to conclude the lemma that we used before by pure equational reasoning. So the point we are interested in is the second part of the lemma. And we show that by first using the first part of the lemma, which already requires unique choice, and then doing some more steps that you don't have to understand fully, we can reach the desired result. And since on the way we used unique choice a bit, this means that the full lemma requires unique choice, and by this that also the theorem in this way requires unique choice. And this is of course a situation where one might be not completely satisfied. And so we also show, and I will quickly summarize how this works, that assuming unique choice here is inessential, and it's just due to the fact that cardinality comparisons were based on functions, which are type theoretically something different from total functional relations. So what we can do is just introduce the weaker notions of cardinality comparisons based on total functional relations, and then the critical bijection from before can be proven without unique choice, because it's easier to establish total functional relations. Here, this now just requires excluded middle as before. And since we now can prove this lemma, we can look at Sierpinski's theorem. For this, we will have to reformulate the statement a bit. So GCH will now have the weaker comparisons, the ones based on just relations. And the axiom of choice will not state the existence of a function, but just the existence of a subrelation. So this is again a weaker form. And then Sierpinski's theorem in this formulation can be proven without appealing to unique choice. Okay, so this finishes the technical part of the talk, and I want to end with 2 more slides. The first slide about take-home messages, what I want you to take home from this talk. The first thing is that whenever one wants to mechanize set theoretic results in a type theoretic systems, one has a choice on which level one does this project. And this choice is a bit restricted by what one is doing. So for instance, if one wants to do actual meta-theoretic results for set F set theory, then probably there is no way around using a first-order axiomatization, because only then you have access to syntax inspection and concrete model constructions. On the other hand, if you do something internal, it might well be that you can use higher order set theory and have an easier life, because then you can use a lot more of the type theoretical expressivity. And it could also be that the theorem you're looking at is not so much a theorem of set theory originally, but it's just a theory of any foundation being expressible enough to represent the notions involved. So in particular, it could be that it's just a type theoretical result. And by this, you are spared all the work in connection with an intermediate axiomatization. The second take home is that in this setting, higher order set F is a bridge between both worlds. So you have set theoretic notions present, you have the primitives guaranteed by the axioms, you have notions like ordinals available. On the other hand, you inherit a lot of the type theoretic structure that is ambient, and so it makes your life easy because you can write down things on type level instead on in set level, or even in first order logic. And in the final slide, I want to just hint at some open questions that were left. So the first thing is we were actually interested in finding whether Sierpinski's theorem is constructive, so whether GCH implies AC without using excluded middle. And we were not able to finish this proof. We were able to localize the use of excluded middle a bit. In particular, we could escape using the Cantor-Bernstein theorem a couple of times. But still, in the intermediate constructions, you will have to show that some sets or types are well ordered, and it seems that all these intermediate proofs are even equivalent to unique to excluded middle. On the other hand, it could be that this whole proof strategy is just unnecessary, and that there is a completely different idea that works and goes through constructively. And then, because AC implies excluded middle, this would in particular mean that GCH implies excluded middle. So it's a really very classical principle. The second open question would be to look at the situation in other proof assistants and type theories. And here what we think so far is that in pure Martin-Löf type theory, it's a bit hard or even impossible to easily write down set theoretic results, because here you do not have propositional existence or power sets. And in general, on the other hand of the spectrum, too rich type theories that prove, for example, the axiom of choice, do not entail a meaningful statement anymore for Sierpinski's theorem. And what we think, and I would be really interested in looking at this in more detail, is that in homotopy type theory, you can represent set theory even better than in Coq, because, and in some sense more uniformly, because you do not have to extend Coq with ad hoc axioms, because extensionality holds uniformly by the univalence axiom, and unique choice is provable by the notion of homotopy propositions. So it would be really interesting to do this proof and maybe some other set theoretic or set theory inspired results in homotopy type theory. And a last question could also be to investigate how much the levels available are connected. So for instance, how much of GCH, if you assume it in the Z level model, would leak out into the type level. All right, so I want to leave you with this slide showing the main references we have used, and I'm really looking forward to seeing you in the discussion. So thanks for your attention.